Okay, we find a line through the point 0, 6, 13 parallel to the vector negative 4i plus 6j minus 6k. Well, what does it mean for a line to be parallel to a given vector? A line through a given point to be parallel to a given vector. It simply means that if you take the point 0, 6, 13 and a point x, y, z, that point x, y, z will be on the line provided that the vector from here to here is parallel to the given vector. So that we have the vector, the white vector here, 4i plus 6j minus 6k. The question then is whether this vector, which is x minus 0 times I, plus y minus 6 times j, plus z minus 13 times k, is parallel to this. So we conclude that x, y, z is on the line if and only if this vector, the purple vector up here, is parallel to this vector, our given vector. Now, what does it mean for a vector to be parallel to another vector? Well, this vector is parallel to this if and only if each vector is a constant multiple of the other. Which has, so if and only if either vector is a constant multiple of the other. Okay, so if each vector is a constant multiple of the other, but if either vector is a constant multiple of the other, say the constant multiple is 7, then that other vector would be 1/7, the reciprocal multiple of the original vector, okay? So, we'll let t be the constant multiple, the multiplier. That wasn't really a very good way to say that, because constant multiple would be another vector. So we'll say that's our constant multiplier. Let's MULT could stand for multiplier, and maybe it did when I wrote it. It's been a while. Okay, well, in any case, if that's the case, then this vector would have to equal t times this vector. Meaning what? Meaning that x, the coefficient, or the coefficient of I here, has to equal the coefficient of I here, which is negative 4ti. So x has to be negative 4t. Okay? And then y minus 6j has to equal 6j, so that y minus 6 has to equal 6, meaning that y is going to equal, y minus 6j is going to be t times 6j, which is 6t times j. Y minus 6 will then be 6t, so that y is going to be 6t plus 6. And similarly, we get z minus 13 equals negative 6t, so z equals negative 6t plus 13. This is the equation of our line. So, again, line, now wait a minute. I just changed gears over here. Okay, this is the equation of our line, and it's really three parametric equations, three equations in terms of the parameter t. Okay? Over here now, we do a line through 0, 6, 13 that's parallel to the vector 4i plus 2k. Now, where do these vectors 4i plus 2k and negative 4i plus 6j minus 6k come from? Remember, we had our figure where we measured the lengths of the edges that gave us the coordinates of 3 points on the sloped surface of this object, okay? And this is one of the vectors that we got when we took the cross product of two of our vectors. This is another vector that we got when we took, I'm sorry, this is one of the vectors that we got for one of these edges. This is the vector we got for another edge. So now we've got a line through 0, 6, 13. If this is our point 0, 6, 13, we've got the equation for this line. Then we get the equation for the line parallel to one of our other sides. I don't remember if this was the other side. Parallel to this vector, okay, which is a vector along one of these edges. I'm saying side instead of edge. I should be saying edge. Sides are flat surfaces. Edges are just line segments, essentially. Okay, anyhow, line through this parallel to this. By similar reasoning, the statement is, well, again, we have the vector xi plus y minus 6j plus z minus 13k, but in this case, it's equal to t times 4I plus 2k, because now this vector is said to be parallel to this vector. And we get our three equations here, and that would be maybe our three equations here. So that might be this line, the line through this edge. Now let's verify that our equations for the line, our parametric equations for the lines, are consistent. So we do that by finding the point of intersection of these two lines. Now the point of intersection had better be 0, 6, 13, because that's the common point that we use. Maybe that's this corner, maybe it's a different corner. In any case, we have equations of two lines, assumption being both of those lines go through the point 0, 6, 13. So the question then is, if I give you two equations, how do you determine if they intersect? Well, they intersect if there is some value of t such that the x, y, z here is equal to the x, y, z here. Now, it's not necessarily the same value of t. In this case, it turns out that it is, so I don't want to get to that. The question is there u that we could use in place of t here, such that there's a value of u here and a value of t using the t's here, so that these x, y, and z coordinates are the same. And we talk more about that a little bit later. In this case, though, we can set up x equals x, giving us 4t equals negative 4t, y equals y, giving us 6 equals 6t plus 6, and z, 2t plus 13 equals negative 6t plus 13. If we do this and solve these equations, we find that t equals 0. T has to equal 0. And these equations can be solved by reducing a matrix or by doing any of a number of things. Okay? In any case, when t equals 0, this is equal to this. Because when t equals 0, x is 0, y is 6, z is 13. That's 0, 6, 13. Here, again, x is 0, y is 6, z is 13. Okay, more on that later, but this proves at least that these two lines do intersect at this point.